Still, after 2 years, I'm not familiar with, this is stuff. I prefer the board chalk. Hopefully we go back to normal soon. Okay, let's go back to RKHS, different methods that we can produce K positive. And K positive gives us a space H of K. Here we want to consider kernels arising from polynomials. Or a power series. So we start with polynomial for which there is no convergence problem, but then with a little bit of work, we can go to power series. So P of X equal to sum n from 0 up to fixed n, a n x n. And the main assumption is that a n is bigger than or equal to 0 for all n. That's the main assumption. Then we consider K index P from, no, not from C, from C2 to C by this formula. Kp of Z and W is defined by sum an ZW bar, the combination that we had before, exponent n. In other words, it's P evaluated at point ZW. That is why we call it Kp. So it's P evaluated at ZW bar. And the claim is that Kp is positive. Even though it's trivial for us now, but Kp bigger than or equal to 0, it means as a kernel. And this is equivalent, so this is equivalent to say that for any Z1, Z2, Zn in C, if you consider the n by n matrix, Kp, Zi and Zj, Ij from 1 up to n, it's not the same n as above. Well, it's better not to mix this n with the other ones. For any m, this is bigger than or equal to 0. And why is this the case? First of all, we have seen this before, at least when P is a polynomial of degree 1, when just P of Z is equal to Z, ZW. We have seen this before. But in the general setting, what do we obtain? If we do the calculation, replace Kp by this formula you see immediately that this matrix is equal to A0, a matrix GM, plus A1 Q plus A2 Q on Q, the short product of Q with itself, and finally AN Q on Q on Q n times. Where Q is simply the matrix Zi, Zj bar. This is the special case that we have seen before and corresponds to the special case P of Z equal to Z. We know that this is positive. I mean, Q is, we know Q is bigger than or equal to 0. And Jm is a matrix, all of its elements are equal to 1. And also this is positive. And why now there is a place you see why we assume that the coefficients are also positive. We use Shor theorem. Shor theorem tells us that if Q is positive, then Q, Shor product of Q, doesn't matter how many times, K times, is also positive. So every matrix here is positive. The coefficients are also positive. And therefore, since Aj are also positive, we conclude that Kp, Zi, Zj is positive. And therefore, Kp is a kernel function. And again, by Moore theorem, which we discussed in detail, we have a functional space, which we call it HKP. And there is a way to find some of its elements. The way is hidden in this observation. Kp of Z and W is the sum n from 0 up to n, an Z W bar to the power n. And since an is positive, I can write an equal to root an squared and consider root an with Z and with W. So so I define Fn of Z to be root of an Zn, and Kp Zw becomes sum from 0 up to n, Fn of Z, Fn of W bar. That's a very precious representation. The reason is that in the book, there is an exercise, which I believe it should be a theorem. It's an improvement of a theorem which we proved earlier. We proved that if Fn is a Parseval frame, then we have this identity. So the theorem we had, so recall if Fn is a parsable identity, then K or Kp in any case, Z and W has this representation. However, when we say is a parsable identity, it is hidden in the assumption that Fn is an element of the space H. It's already there. And then we have this identity. What is in the exercise, which is very more important, is that we do not make this assumption. We just say that Fn are functions. On the space X. So we do not assume that it's part of conclusion. That's the important part of that exercise. So we have some function. Our assumption is what we have here in the red box. The assumption is that for each Z and W, Kp of Z and W is this series of complex number. Here is the finite case, but it can be infinite too. Fn of Z, Fn of W bar. And the conclusion is that that's the important part of the conclusion. It's in this space. And even we can say something about its norm. And Fn is a parsable frame. In the finite dimensional case, which is, let me write it in the more general setting. Why just finite? Let's put it here, infinite. Even in the infinite, this is true. If we are in the finite dimensional case, we can say a little bit more than parsable frame is an orthonormal basis. The only thing we need to assume here, which causes, the little problem, is that probably some of these Fn's are identically zero. But this is something trivial that we can remove. We can assume that Fn not equal to zero. Otherwise, even if Fn is zero, still this is true. In frames, we can have, element can be dependent. So being zero is acceptable here. But if we want to end up with a parsable, with an orthonormal basis, we need to assume that they are not zero. So it's not something, a big assumption. This is needed here in the box formula. We have K of P is equal to this. We do not know if Fn are in this space, but this observation, which I invite you to prove, and the proof I give a hint, is based on the theorem, which I called it finite controlled interpolation. part 3 of that theorem helps us. Based on finite controlled interpolation, it's very easy indeed to see that Fn are in H and they form an orthonormal basis. And here we have Kp, Z and W is equal to sum J n from 1 up to n, Fn Z, Fn W bar. Fn of Z is root of Rn Zn. And here this assumption comes into picture, this one. If An is equal to 0, well, then Fn equal to 0, and well, it's trivially Fn is in this space, nothing important here. But if we consider the set of Fn such that An not equal to 0, which is the same as the set of Zn such that An not equal to 0. This is a set, this one, better not to, because I want to have something normalized. I write it this way. This set is an orthonormal basis for H of Kp based on the above theorem. And also we can say that Zn is in K, H of Kp if An is not equal to 0. So that's the way we can create a function space. It's not trivial. It needs a little bit of work here to replace this if by if and only if. In other words, it's bidirectional. It's a bit of work. It's not trivial, but I don't need it here. A bit of generalization of the previous idea. It's power series instead of polynomial. So we consider P of X or P of Z equal to sum n from 0 and now up to infinity An Zn as before An bigger than or equal to 0. There is a problem of convergence. And now to deal with that, I assume that this series is convergent on a disk of radius R2. You may say that why not a disk of radius R? It's okay. If you want to go with R, go ahead. But later on, you will have root square of R somewhere. Because in future, I want to have R. I replace the R here by R2. And that root square of R2 becomes R. So it's just a matter of notation to be more convenient in future. So I have a power series, which is convergent on a disk of radius R2. And then I define Kp of Zw by n from 0 to infinity An Zw bar n. And be careful here, not for all Z and W. Z and W is in a disk of radius R. That's why I put R2 over there. And now what can we say about, the claim is that Kp is a kernel function, is bigger than or equal to 0. So this is the same thing as if you consider Kp, Zi and Zj, I and j from 1 up to m. For any m, that's a positive matrix. This is immediate based on the preceding example because we can consider Pn to be the same sum, but n from 0 up to n, an, zn. And we know that Kpn is positive, which is equivalent to the fact that Kpn Zi, Zj, I and j from 1 up to m is a positive matrix. It's a matrix with m2 elements. And now what happens if n goes to infinity? If n goes to infinity, for each I and for each j in this between 1 and m, Kpn Zi and Zj converges to Kp Zi and Zj. And if you write the definition of this, the definition is a sum being bigger than or equal to 0, a finite sum. In a finite sum, you can change the order of limit and sum. And when you change the order of limit and sum, you immediately see that this one is also positive. So immediately implies that Kp of Zi and Zj is also positive. So we have a positive kernel, we apply more, and as before, we have h of Kp. Previous result, if I write Kp of Zw as sum, n from 0 to infinity, fnz, fnw bar, when fn of z is root n zn. The previous observation says that if an is not equal to 0, this implies that well, yeah, this all the time for any n. For any n, the previous observation says that fn is in h of Kp, but it is important when n is an is not equal to 0. So for any n such that an not equal to 0, we conclude that Zn is in h of Kp, not for the other values. And also the set of fn such that an is not equal to 0, this set is a Parseval frame. If I remove this and write n bigger than or equal to 0, still it is true, but it is not that useful because you can put the elements which are 0 away. And there is one little problem, which is the difference between the finite case and infinite dimensional case. If we have a Parseval frame, and even here we remove the zeros, we just consider those which are not 0. Can we conclude that we have an orthonormal basis? Not really. We need another notation which doesn't appear in linear algebra, but it is more for operator theory. Here is the definition. So H is a Hilbert space. And Fs with some S in set of elements in H. We say that this set is L2 independent. L2 independent if whenever some S in S ASFS is equal to 0 and this is in L2 of S. Then we conclude that AS is identically 0. In other words, for any S is equal to 0. The only way that this can be 0 is that the coefficient be 0. This is not the same thing as independent that we have seen before. Let me give an example to distinguish things. Of course, L2 independent implies independent, but not vice versa. Example, consider the ordinary L2, the little L2 that we have as our first Hilbert space with En n bigger than or equal to 1, the canonical basis. And then consider this element, X sum n from 1 up to n, 1 over n En. This is well defined because 1 over n is in L2. So X is, what's happened? So X is also in L2.
I think you want the upper limit of the sum to be infinity rather than n.
Yes, thank you. Yes, indeed. And I really need that infinity. We'll see momentarily. Now, first claim. The set X, E1, E2, E3, and so on, is independent. And the second claim is that the same thing is not L2 independent. Well, proof, not that difficult. Assume that a finite linear combination of these elements are 0. Without loss of generality, we can say that lambda times x plus lambda 1x E1 up to lambda m Em equal to 0. Because even if some elements are not there, we can consider the corresponding lambda to be 0, lambda k to be 0. So this can be a general linear combination here. And now look at the component m plus 1. This is a vector. This is a vector. It has first component, second component, and comes up to component m plus 1 equal to 0. What is this component? Do you agree with that? Because for E1 up to EM, I mean, this is the first component equal to 1, the rest 0, and the same for E2 up to EM. So all the component here from m plus 1 up to infinity for all of these are equal to 0. So the only thing which remains is lambda times x, which gives us lambda times m plus 1, lambda over 1 m plus, lambda over m plus 1 for this position. And being equal to 0 implies that lambda equal to 0. And then we come back to lambda 1 E1 plus lambda m EM equal to 0. They are independent, implies that lambda 1 equal to lambda 2 equal to lambda m equal to 0. So it's, they are independent. But why are they are not L2 independent? Because simply consider 1 minus 1 times x plus 1 times E1, 1 over 2 times E2, and so on. The sequence we have here is the sequence minus 1, 1, a half, 1/3, and so on, which is in L2. And the combination is equal to 0. So it's a non-trivial combination. Which gives 0. So therefore, they are not L2 independent. I mean, you can imagine something naive, but you can imagine like this. This is independent. I mean, the set of all independent vectors. L2 independent is smaller. Is like this. There is another notion which is used in some books, for example, in books in wavelet theory, omega independent. And in omega independent, they even do not assume that the coefficients are in L2. So it's something even smaller, omega independent. I don't use this, I just use the L2 independent. And to finish today, the reason I need this notion is this proposition, which says that let Fs, S is in S, be a Parseval frame for H, for the Hilbert space H. Then Fs is an orthonormal basis, is an orthonormal basis for H if and only if is L2 independent. This is a property between, I mean, in operative theory, which is hidden in these words. When you look at the proof, you will see immediately what's going on. Proof, I have a few minutes. I can finish the proof. This part, trivial. And now we work for the other parts. Consider the vector v that we had before from L2. No, v was the other way around. V was from H to L2, L2 of S. By this definition, V of an element H was defined to be this vector, H inner product with ES, S is in S. That's the way we defined V. We saw this before. And this is an isometry. Isometry is the same thing as Parseval frame. I mean, that's why I said facts from operator theory are hidden here behind the words. Parseval frame is the same thing as this mapping is an isometry. That's the first thing. We saw also, or it's very easy to compute, the V star. V star is from L2 VES to H2. And it maps ES to FS. That's, I mean, very easy to see. And indeed, I already did it. And again, another thing which is hidden behind the words, if you look carefully, L2 independent is precisely the same thing as V star is injective. Because when you look at V star of the sum over SAS ES, it's the sum ASFS. And L2 independent says that when this is equal to 0, all the coefficients are 0, therefore this element is equal to 0. In other words, the only element which is mapped to 0 is 0, so it's injective. And this argument is, or this explanation is reversible. So when you look carefully, you see that's another fact which is hidden, fact from operator theory, which is hidden behind the words. L2 independent is the same as the injectivity of VS. Last fact, N, the null space of V star is equal to the range of V perp. And what do we want to prove? We want to prove that L2 independent implies the orthonormal basis. So L2 independent implies that V star is injective, which is the same thing as null space of V star is equal to just 0. And this implies that range of V perp is equal to 0. And remember, it's a frame, Parseval frame, the range is closed. So the range of phi is equal to H. And indeed, I mean, if you want, you can also go backward. But I need just into this direction. The range of V is equal to H. Go above. range of V is equal to H. So what do we have here? V from H into L of S. So resume, or I mean, of what we have up to now, we have V from L to S to H. We know that it's onto, and we know it's injective, and we know it's an isometry. So all of this now, the only thing was missing was this one. And so it's a unitary map. And having a unitary map means that V maps an orthonormal basis into an orthonormal basis. So we are done. Well, I wrote these things about V. Yeah, it's true. It maps. Sorry, this is V star, not V. Range of V. Yes. So V is unitary. V star is also unitary. So V star maps ES to FS. Therefore, FS is an orthonormal basis. Let me put it more correctly. What I wrote here was correct. So V is unitary map, and therefore V star is also a unitary map. And now I use V star here. End of story. Well, that's why we studied L2 independence. And so we could obtain some power series of, kernels defined by power series. And therefore, the theorem that we had before, this is my last, sorry, a bit more than, let me finish with this. We had Kp of Z and W sum n from 0 to infinity an ZW bar to the n, which we can write as before, Fn of Z, Fn of W bar. And now we can, based on the above observation, we can say that the set of Fn when An is not equal to 0 is an orthonormal basis. We already know, so fact 1, we already know that this is a Parseval frame. Even if we remove this, it's already a Parseval frame. The only thing we need to establish to obtain an orthonormal basis is to show that they are L2 independent. But for that, assume, say, lambda n, not to mix with the other one, is in L2, and consider the sum of lambda n Fn over An not equal to 0 in that H. So the convergence is in H, but we know that convergence in norm implies pointwise convergence. So this implies that the sum over An not equal to 0, lambda n Fn of Z equal to 0 for any Z in dr. And let's write this sum. Usually at the end doesn't like what I write. Okay, it's okay. An not equal to 0, lambda n an root of this Zn equal to 0 for any Z in T R. And now we use our knowledge of complex analysis. On a disk, we have a series which is identically 0 for any Z. So this implies that all the coefficients are 0. Lambda n root n is equal to 0. If instead of an not equal to 0, I've written n from 0 to infinity from the beginning, everything was okay, and here you can still I can say for all n bigger than or equal to 0. But I cannot conclude that lambda n's are 0 because probably some of an are 0. That is why I assume that over all indices such that an not equal to 0, and I finish with lambda n equal to 0 for all of them. So this is L2 independence. And L2 independence by previous theorem means that Fn not 0 is an orthonormal basis finished. We obtain a basis for our space too. Almost at the end of this chapter 4, but I mean, I will continue next week to finish this chapter and go over chapter 5. Thank you very much. Hope you liked it.